Alright, this is the final video in the electrochemistry unit for grade 12 chemistry. We're taking a look at electroplating and quantitative electrolysis kind of questions. Just to review, we said at the end of the last video that electroplating is where you are taking a more valuable metal and plating it, coating it, using it to coat rather, a cheaper metal surface. So in this example in the diagram here, we have somebody with a key that has been immersed in a solution of copper 2+. So here is Cu2+, a blue colored solution. And we are interested in plating the key with the more valuable copper coating. So we're going to take the key, which maybe is made of iron or something like that, and we're going to end up with a thin layer of copper metal on the surface of the key. So to do that, we've connected the key through a wire. Now over here we have something we don't usually show in our diagrams. It's just a switch. Right now it's an open switch, but when we close it, the circuit will be completed, so we can ignore that. But we notice that it's connected here to the negative terminal of a battery. In this schematic way of representing a battery, the smaller dash is a negative terminal, and the longer dash is the positive terminal. So we've connected the key to the negative terminal of a battery. So we're going to be doing a type of what's called electroplating. The electrons are going to come out of that negative terminal of the battery, and they're going to head through the wire this way and flow into the key. The key is going to then acquire a negative charge because of the electrons coming in, and that negative charge will attract the copper 2+ cations. So the cations are going to the cathode. Remember that the key, the thing that we're trying to plate, has to be the cathode where reduction happens in the cell. The other electrode is a piece of copper metal, and it's there simply to replace the copper ions which are being deposited on the key's surface. So as the copper ions go and get electroplated, as they plate the surface of the key, more copper ions are going to come out of the copper strip to replace them, because the copper strip will be oxidized. So copper there is going to turn to copper 2+, or at the surface of the key, copper 2+ is going to become copper metal. So copper is being oxidized at the anode, copper is being reduced at the cathode. And of course the electrons from the anode will flow back out this way. So the copper strip on the left is the anode, and the key is the cathode. What we're going to do in this video is take a look at some quantitative mathematical problems that are going to be solved using unit multipliers predominantly. Having said that, there's one formula for those of you who really like formulas that you might want to note. This is a formula from a physics class. It says Q equals IT. So Q is equal to I times T. Q stands for charge. The charge, in this case, moving through the circuit. Of course, the charge is carried predominantly by electrons in the external circuit and by the ions moving in the internal circuit within the cell. Now, charge is measured in a unit that, if you haven't taken a physics class, you're probably not that familiar with. It's called coulombs, capital C for abbreviation. Those are the units of charge. So in the formula, Q stands for charge, and charge is measured in units called coulombs. The symbol I in the formula stands for current. Current is measured in units called amperes, or some people shorten it to amps. And current, if you rearrange this formula, you can see a simple definition of current. Current will equal charge divided by time. So in other words, current is how fast charge will be flowing through your circuit. So if you have a current of 10 amperes, that means the charge is flowing at a rate of 10 amperes per second. So 10 coulombs per second will be the rate at which the charge is flowing. A 5 amp current means the current is flowing at 5 coulombs per second. Okay, now that's very important to remember. Okay, a 10 amp current would mean 10 coulombs per second, a 2 amp current, 2 coulombs per second. Notice when you switch it to that language, 2 coulombs per second, it sounds like a unit multiplier, which I'm going to make use of when I set up my answers. T in the formula stands for time, and time in this formula has to be measured in seconds. So if a question gives you minutes, you'll convert the minutes to seconds. If it gives you hours, convert the hours to minutes, and then minutes to seconds. There's one other concept which is new to us that's very important for solving these problems, and that's called the Faraday, named after Michael Faraday, a British scientist in the early 1800s who played around with batteries and discovered lots of important relationships. The Faraday is the amount of charge measured in coulombs carried by 1 mole of electrons. Okay, the amount of charge per mole of electrons. So 1 mole of electrons has a charge of 96,500 coulombs. Now in your data booklet, on the second page, if I recall, at the top, you'll see that the Faraday is shown there, and I think it has more significant digits than this, but you might want to just take a look to be sure you know on a test if you forgot what this number was. It is in the data booklet. It's actually on page 3 at the top. The Faraday is shown there as, in scientific notation, 9.649 times 10 to the 4 coulombs per mole. So 9.649 times 10 to the 4 means 96,490, which is pretty close to 96,500 that I've written here. Now on the left of this slide, this is not something I personally would copy down. It's just a flow chart for those of you who like to sort of memorize steps in solving a problem. You might want to copy that down, but I'm going to see that these steps simply flow out of the units in the question. So I don't ever even think about this kind of flow chart, but if you like to use formulas instead of unit multipliers, then maybe memorizing this flow chart would be useful, but then you're memorizing things, and that means you'll be confused on a test or exam, and I really discourage it. Okay? So let's jump in to take a look at a sample problem, and we're going to use this concept of the Faraday very much. So make sure you know that. There's 96,500 coulombs in a mole of electrons. Alright, so this first example, we're going to look at 3 types of problems. In the first type, it's a problem where we're calculating the amount of a metal that will be deposited. Now, amount could be asked in terms of moles, but in this question we're going to ask in terms of mass. So what mass of aluminum metal, and in the picture we saw earlier it was copper metal being plated, now it's going to be aluminum. What mass of aluminum metal could be produced in 8 minutes, 8.00 minutes, sig figs, by passing a constant current of 100 amperes through a molten mixture of aluminum oxide? So the scenario here is a little bit different. We're not simply putting a key in a solution of aluminum and depositing it, but we have a molten aluminum oxide. We're going to do electrolysis, and the aluminum will be deposited at the cathode. So we're going to, in the same way, calculate the mass of aluminum that can be deposited. Now, one of the things we need to consider is the half reaction responsible for depositing the aluminum. Notice in this formula for aluminum oxide, what's the charge on the aluminum? Can you stop and think about that? What charge does that aluminum have? If there's 3 oxides bonded to it, what's aluminum's oxidation state there? Once you've got that, write yourself a half reaction that shows that aluminum with its charge becoming aluminum metal. Okay, so you should have written something like this. Aluminum 3 positive will gain 3 electrons to make aluminum. In other words, 1 mole of aluminum, this is going to be an important unit multiplier later, 1 mole of aluminum needs 3 moles of electrons. Okay, so 1 mole of aluminum needs 3 moles of electrons. That will be a unit multiplier we're going to use later. All right, let's jump in. Where do we start in this problem if we're trying to find the mass? Well, we've got two numbers in the question. We have a time and we have a current. Now the current, we remember, is actually a unit multiplier. Current, we remember, in this case 100 amps, means 100 coulombs per second, or in 1 second. So we have a general rule that we don't start the answer using unit multipliers. So don't start your answer with the current. Well, then that leaves the time. So let's begin the answer with 8 minutes. Now, if you remember, we said that you have to use seconds in these problems. So the first thing I'm going to do is get rid of minutes and convert to seconds. Now, if you're doing this with me, see if you can predict what I'm going to do next. What will be the next unit multiplier? What will I get rid of, and what can I convert to? Okay, now if you focused on the current, you've got it right. We have seconds at this point, and the current was 100 amps, which means 100 coulombs in 1 second. So we could get rid of these seconds right here, and we could convert seconds to coulombs of charge using the current, 100 coulombs per second. Now, if you're using formulas, if you think of the formula we saw earlier, what I've just done is I've multiplied the current, I, by the time, t. And so in that formula it said Q equals IT. So when we multiply these things, we get charge, which is what we have here, coulombs. And notice we didn't stop to think about the formula at all when we did this. All right, so now where can we go from here? Do we know anything else that involves coulombs? Well, if you remember on the previous slide, there was that concept of the Faraday. There's 96,500 coulombs of charge carried for every mole of electrons. So we can convert coulombs to moles of electrons. Okay, 1 mole of electrons has 96,500 coulombs of charge. Okay, remember with unit multipliers, you focus on the units first, then you put the numbers in. So I needed to put coulombs in the denominator there to cancel with the coulombs that were in the previous multiplier. And then the thing I was converting to goes on top, the moles of electrons. As I put the numbers in, I say the relationship to myself to make sure I don't put the numbers in the wrong place. 1 mole of electrons carries 96,500 coulombs of charge. Now, what can I do with moles of electrons? Well, if you think about the half reaction that we just looked at a minute ago, 3 moles of electrons will produce 1 mole of aluminum. So we can switch from moles of electrons to moles of aluminum. A very common mistake is to forget this unit multiplier. And the reason people forget it is that they forget to put in the previous multiplier not just moles, but moles electrons, right? When I put moles, you might be tempted to switch moles directly to grams without realizing that that wasn't moles of aluminum, it was moles of electrons. We have to get rid of moles of electrons and switch to moles of aluminum using the half reaction. Now we're pretty much done. The question wasn't asking us how many moles of aluminum, it was asking us how many grams of aluminum. So the last unit multiplier is just the molar mass of aluminum to switch to grams. You might want to write underneath your unit multipliers what they represent so that when you're studying, this will make more sense to you. So 100 coulombs per second, that was our current, 100 amps. The 1 mole of electrons, 96,500 coulombs, is the Faraday that we just were introduced to. The moles of aluminum to moles of electrons, that comes from the half reaction, the 3-to-1 ratio that was there. And then finally, the molar mass. Grabbing a calculator and evaluating that, 4.47 grams of aluminum would be produced in this electrolysis problem. All right, let's take a look at a second problem where instead of looking for the amount of product, we're going to look for how long it would take. So in this question, we're going to be given some different information. Let's jump in and take a look. How many minutes will it take to deposit 10 grams of copper metal from a solution of copper nitrate using a current of 5 amps? If you think you know what you're doing here, this is sort of the reverse of the previous problem if you think about it. If you know what you're doing, pause the video and try to set up your unit multipliers. Keep in mind that because the copper nitrate has 2 nitrates attached to copper, the copper there must have been copper 2 positive. That's important because it means the half reaction is copper 2 positive gains 2 electrons to make copper, and therefore 1 mole of copper needs 2 moles of electrons. Also remember that a current of 5 amps means that there was 5 coulombs of charge traveling through the circuit in every 1 second. 5 coulombs per second is what the current meant when it said 5 amps. That's going to be a unit multiplier. So what should we start with in this problem? Well, we know we're not going to start with the current because that's a unit multiplier, and we'll use it to convert things. So that means there's only one thing we could start with here, and that's the grams of copper. So begin with 10 grams of copper. Now what can you do with that? Pause the video and set it up. Okay, if you said switch grams to moles, copper, pretty good. Now make sure you didn't just say moles, you said moles of copper. Okay, now where can we go with moles of copper? Well, if you're thinking the half reaction, you've got it right. The half reaction says 2 moles of electrons will make 1 mole of copper. So we can get rid of moles of copper and we can switch to moles of electrons. Why would we want to do that? Because we have the Faraday. Remember, the Faraday said there's 96,500 coulombs of charge for every mole of electrons. So we can convert the moles of electrons into coulombs of charge. And finally, using the current, 5 coulombs for every 1 second, we can convert coulombs into seconds. But the question didn't want seconds, it wanted minutes. So we'll do one last multiplier, we'll get rid of seconds, and we'll convert to minutes. There's 60 seconds in 1 minute. So grabbing a calculator and evaluating all that, you'll find you need 101 minutes to deposit the 10 grams of copper in with a current of 5 amps. There's one final type of common electrolysis problem. For the first one, we asked, how much product can you make? In the second one, we asked, well, how long would it take? The third variation of these problems is to ask, what current, how much current would you need to perform the electrolysis or the electroplating? So here's a typical question. What current would you need to deposit 5 grams of zinc metal from a solution of zinc chloride if you have 1 hour to work with? So in 1 hour, you've got to deposit 5 grams of zinc. What current would you need to do that? Again, let's stop and think about the formula here. Zinc chloride, ZnCl2, means that the zinc must start off with a charge of 2 positive. So there's going to be 2 moles of electrons for every 1 mole of zinc metal. Now where can we go from here? What will we start with? Well, it might seem like a 50-50 choice. Should we start with the 5 grams of zinc and go to moles of zinc, etc.? Should we start with the 1 hour and go to seconds? Well, if we think this through just for a minute, we need to find current, and current is charge over time. Charge over time. So why don't we go and find the charge, then we'll divide by the time at the end. So we're going to end up using the time at the end of the problem. So let's take the 5 grams of zinc as our starting point. See if you can take it from here. Where are we going to go? Predict each unit multiplier. Okay, if you thought we'll switch from grams of zinc to moles of zinc using its molar mass, that's a good idea. Now what? Well, we have a half reaction, and in that half reaction we know there's 2 moles of electrons for every 1 mole of zinc. So we can switch moles of zinc to moles of electrons. Now what? Well, moles of electrons, we've got the Faraday. The Faraday tells us there's 96,500 coulombs of charge for every mole of electrons. So let's get rid of the moles of electrons and switch to coulombs. And notice that's an important point because charge is part of the definition of current. Current was charge divided by time. So if we take this charge, all we need to do now is divide by the time. Now the time was given as 1 hour. So I'm just going to go ahead and divide by 1 hour. Now we have a small problem. The current here would be coulombs per hour, but the definition of current should be coulombs per second. So let's get rid of hours and replace it with seconds. And there we have it. If you look at everything that cancels, the grams of zinc is gone, the moles of zinc is gone, the moles of electrons is gone, coulombs is not gone, there's nothing to cancel coulombs, hours is gone, and seconds is left. So what we have is coulombs on the numerator, seconds in the denominator, coulombs per second, which is amperes, which is current. So we get the answer 4.1. Now if you wanted to leave it as coulombs per second, that's fine, but remember coulombs per second is the same as amperes. So 4.1 amps would be the current needed. So those are 3 common types of electrolysis problems, all solved with a string of unit multipliers. The tools you have are the Faraday, there's 96,500 coulombs per second, per mole of electrons rather. The half reaction relates the moles of electrons to the moles of the element you're talking about. Remember that current, if you see current in a question, 10 amps, it means 10 coulombs per second. Those are the tools you have, and the rest is basically unit multipliers.